Today we're going to take a look at models. We had talked about incidence geometry last time, and we're going to build upon that and talk about how we would interpret our incidence geometry ideas. So to start with, an interpretation of an axiomatic system is that we give the undefined terms a particular meaning, and we interpret the defined terms after that by substituting in the interpreted meaning. And it'll make more sense when I show you an example of what all that means. So we're going to do an example, and we're going to see if this creates a model. So an interpretation for incidence geometry. Points would be students in here, so each of you. The lines would be your classification, freshman, sophomore, junior, or senior. And incidence means belongs to. So every point, that is every person in here, has a line that they belong to because each of you has a classification that you are in, right? You are a freshman, sophomore, junior, or senior. So part of this feels very much like it stands a chance. But we have to check and actually make sure if the three axioms that we have hold with all of that information assigned to it. Okay, so this can be an example. It just doesn't necessarily mean that it's a model. And we have to see if it's a model by checking our three axioms. Okay, did everybody have everything written down? Did I move too fast? Okay. So this is what I had just said. Modeling an axiomatic system given an interpretation, which is what I gave you, of the system. If all of the axioms are true, when the interpreted meanings are substituted in, then the interpretation is called a model. So that's what we're going to do. We're going to check our three axioms with that interpretation. Points are you guys, your classifications are lines, and incidence means belongs to see if it works. So does the previous example model incidence geometry? Did I move too fast? Yeah. I'm sorry. I'll slow down. Okay, so our first axiom said the following when we substitute in with the interpretations. For every point, and our points are now students, so for every student in geometry, if we have two different students, so if we take Noah and Kennedy, we take Kelsey and Haley, we take Seth and Felipe, two different students, will there exist a unique class that they both belong to? No, not unless you all happen to be in the same class, in which case other things are going to fall apart later, but you're not all in the same class. So this axiom, does it hold for that interpretation? No, it's false. That axiom just does not hold. Now, in reality, we could actually, in some sense, sort of stop. We know this is not going to be an interpretation, but for the sake of actually checking the others so that we can think about them in future problems, we're going to check all three of them, okay? So our second incidence axiom with this interpretation laid upon it says, for every line, which would be our classes, so for every class, there exists at least 2 students that belong to that class. Now, that might work. And I didn't go and look inside a banner and check, so we're going to just see if it holds true or not. My slide's going to say false because I don't think it's true, just in my mind. So let's double check. So how many freshmen do I have in here? And we're done. I didn't think I had any freshmen. So this doesn't work. I already had the freshman class, and it doesn't have anybody in it, correct? Let's just double check the others just so that we know. How many sophomores do I have? Okay, so I have 3 sophomores. Juniors? 3 juniors. And seniors? 2 seniors. So if I excluded the freshman class and I only had lines that were were sophomores, juniors, seniors, this one would actually work, wouldn't it? For every class that actually has somebody in it, there's at least 2 somebodies in that class. When I consider all of the classes, it doesn't work though. So this is also false. The third incidence axiom says the following. There exist 3 distinct students with the property that they don't all belong to the same class. And by show of hands just a minute ago, we found out that that was a true statement, right? For sure, because we had 3 different classes represented. So if I take the right 3 students, right, I will be able to satisfy this incident axiom just fine. This is the incidence axiom that I had mentioned before that would fall apart if you had all been in the same class to begin with, which is what would have made the first statement in this interpretation work. So this statement is actually true for us, as it's stated. If they all said true, it would be a model. But of course they don't. So this is not a model, since it fails axioms I1 and I2.
They were all false. It's not one of those.
Yep. If there's any part of it that's false, it doesn't work. So we almost could have sort of, if we slightly changed our interpretation, we could have gotten I2 to work, right? If we just excluded the freshman class. But the fact that I1 didn't work anyway meant that we were already not going to have anything, pan out for us in the long run. So just fixing I2 to exclude the freshman class still would not have fixed the model overall to be a model. It would have still just been an interpretation that's not a model. Okay, so do you want to see one that works? Because I gave you one that didn't work. You guys played a game a week ago. Some of you found out that you're pretty good at the game, actually, and some of you were like, yeah, this is not working for me. The game is called Set. So the interpretation is that the cards are the points. The lines are the sets. So when you said set and you took 3 cards, you had a line. And incidence is belongs to. So it's on a line if it's in the set. And we're going to check our axioms. I meant to bring the cards. That's not actually what I mentioned a moment ago that I really forgot, but I did mean to bring the cards to kind of remind you, but I think you played with them enough that you can work through this with me. Does set model incidence geometry? I already told you a minute ago that it did. This is going to work. So let's actually check our axioms so that you could see that it works as well. The first axiom, I1, and I've changed again the language to include our interpretation laid upon it. For every card, P and Q, so 2 different cards, there exists a unique set that they both belong to. Now think about it. If I take 2 cards, they're going to have some things in common and some things different. Or maybe they're going to have everything in common or everything different. Well, they're not going to have everything in common, but you know what I mean, right? There's going to be, when you're comparing them, some commonalities and some differences. So maybe they have the same shape, Well, that means that the next card that completes the set has to have the same shape. You're like locked into the specific shape. Maybe their colors are different. If their colors are different, then you're locked into the third item being different, right? And maybe they have the same shading. So they have the same shading, so you're locked into the third card having the same shading, but they have different numbers on them. One has 1 and one has 3, so you're locked into the third card having a specific number. That third card is automatically determined by the first two. If I gave you 2 cards, you should be able to tell me exactly on the board what you're looking for to make it work. Some of you find it very quickly, some of you don't. I don't find them very quickly, actually. I'm not real good at the game. But it determines it automatically, right? 2 cards determine exactly which is the third card it is, and having all 3 of those cards together creates the set, which is our line. So 2 cards automatically create a set once you find the third one, but they automatically tell you what set you're dealing with. So this is true. Every 2 cards that I pick, there's only 1 third card that can go with it. So it's a true axiom. For every set L, so now imagine you picked up a set and you've had them in your hand, you've got those 3 cards there with you. There exists at least 2 cards that belong to L. Well, yeah, like right, there were 3 in fact, we know that. So that one's an easy one for us to check because we played the game. I3. There exist 3 cards with the property that they do not form a set. Oh yeah, in fact, there came a point when Seth had to actually add more than the 12 cards out there because none of us were seeing a set even among 12 cards, right? There is a number, I don't remember what it is, where you absolutely have to have a set once you have them out there, but 12 is actually not a magic number. Not 12, we had 9, didn't we? We started with 9. 9 is not a magic number. You can have, I think it's 15, that you have to have at least 15 before you're guaranteed that it's going to work. But most of the time, 9's enough. Okay? So for sure this one satisfies. This one's easy to argue that this satisfies as well, right? Yeah, lots of options there. So since these 3 axioms hold, this is in fact a model for incidence geometry. You're probably like, but I don't see any lines or points. We played a card game. That's a different interpretation, right? It's not what I thought I was dealing with when I played that game. That's okay.
Did you switch points being sets and lines being cards?
We'd have to go through and check it to see if it would work. So Kennedy wants to know if we could actually let the sets be our points and the cards be our lines. So would every line, every card have 2, let's see how, we have to think about it. So let me just do instance axiom 1 with you. So for every 2 lines, which would be every 2 sets, is there a unique card that belongs to both of them? And I don't think there would be in general, right? Because I can have 3 cards and Kelsey can have 3 cards, and those are 2 lines. 2 points is what you're saying then, 2 points. And there doesn't necessarily have a line between them, a card that they match between. So no, it wouldn't work to switch them. It's a good question. Felipe.
How many axioms do we have to in order to say it's true?
There are 3 axioms, and we've done them all. These are the 3 incidence axioms. So these are the only 3 you check. Now here's what happens. It worked. Because it worked, what we did last time is we had some propositions. I proved 2 of them, and then you proved 3 of them on your homework. Does that sound right? So there were 5 propositions that resulted from those axioms. And if we have a model, which we now do, then those axioms will automatically mean that those propositions hold as well. So here's what's the deal. We can apply the 5 propositions that we proved to the game of set to learn more about the game of set. So I'll read through them, and then you guys can be writing them down. This is what would happen when I take those propositions and apply our interpretation. Proposition 2.1 would say, 2 distinct sets that are not parallel have a unique card in common. And that happens sometimes because you would say, you used my card. I was going to make a different set with that card, didn't you? right? You had intersecting, quote unquote, lines when you did that. And then, you know, whoever didn't say it first doesn't get to have it. But Proposition 2.2. There exist 3 distinct sets that do not have a card in common. In fact, there were lots of distinct sets, right? I had 2 sets, and Shayna had 4 sets, and Felipe had 1 set. And I mean, we had tons of sets, and none of them were in common because that's how we pulled them off the board, right? Yeah, so we at least have 3 of them for sure. Proposition 2.3 says, for every set, there's at least 1 card not in it. Some of these feel weird because we're like, well, yeah, because I played the game and I know that's true. We're not trying to prove it with the game, but we're trying to, you know, in our mind say, yeah, that makes sense. That's what we're doing right now. That makes sense. I agree with that. Proposition 2.4, for every card, there's at least 1 set that doesn't contain it. There's lots of sets that don't contain it, right? Yeah. Proposition 2.5, for every card, there exist at least 2 distinct sets that do contain it. Now that one's a little bit more difficult to sort of picture in our mind because when we pulled it from the board, we eliminated the possibility, right? But think about it. If I had the card that had, you know, red ovals that were solid, the red oval solid card that has 1 on it, okay? Can you picture it in your mind? Looks like the oval, it's solid colored in red, and there's only 1 item on there. I think I got my 4 attributes, and it's an oval, yeah. You can imagine there's lots of other things that will contain it besides whichever one you pulled it off from the board as, right? So maybe it was the one that Seth wanted to pull it off from the board at, but you got him, you know, you got there first. Or maybe it's another one that you even have in your hand that you could have used to pair it with these 2 different cards over here. That's what the last one's telling us. There are other ways that you could have arranged this. And this is why you can play the game over and over and over again, shuffle the cards and get a completely new set, right? Get a completely new game out of it. Because we have these properties, in particular that last one. We have lots of things, lots of sets that particular card could have created. All right, so now that we have a model, we've discovered, or at least confirmed in our mind, that it makes sense that those propositions are true, which they would be. We can also use this model to learn more about the system. Specifically, if something fails to hold in our model, then no proof is possible in our system. You have to be a little bit careful with what I just wrote down. This is a conditional statement. If P, then Q, like you took your quiz on, right? When we talked about conditionals are not the same as their converses. I can't flip this around and for sure make that work. If no proof is possible, does it for sure fail? That's not what this says, okay? Not only that, but it also doesn't say if it works in the system, then there is a proof possible. Our book doesn't define it, but that's actually called the inverse. The inverse is not the same statement either. You have to use the implication as it's written. If it fails in the model, then it's not possible to prove. For example, using the model of set, we know that the statement, there exists a line incident with 4 distinct points, fails. Right? I can't make a set using all those cards that we had that has 4 cards in it. It's not possible. And the reason it's not possible is because we didn't have enough attributes, right? There's not enough different things to compare to make this work. Not enough going on. Thus, this statement cannot be proved in incident geometry, no matter what model we use. And that's kind of a big deal. We're saying it is false, right? It fails to hold in this model, this interpretation that we created. That means that it's going to not be provable in any interpretation that we create later on.
So are we saying that the statement can't be proved? That what we think is false can't be proved?
Correct.
Okay.
Exactly. Exactly. I think I've got one more piece on this paper. Nope, I don't. So you're still writing. Now, just because it can't be proved doesn't mean it can't happen, right? It just means that we're not guaranteed that it will. So could I have 4 points? Well, it doesn't say I can't. It just says that I can't prove that they are going to be 4 points. Do you see the difference? I can't prove it's going to rain tomorrow. I can speculate, I can whatever, but I can't prove it. Doesn't mean it's not going to happen. I just can't prove that it will. Okay? So, taking one of these statements and changing it, I told you we can't use, we need to use our logic, things that we've done before, to make sure that we're interpreting this sentence right. If something fails to hold, no model or no proof is possible. But if it's true in the model, it also might not be provable. Just because something is true for the model that we have created, that it worked in all the axioms, all that good stuff, it's true in our model, it not necessarily is provable in the system. In fact, it might not be true in the system in general either. And an example of that is, we didn't count them, but using the model of set, there are actually 81 cards. So you might be led to think that means that any incidence geometry would have 81 points, just because set has 81 cards. And that's actually not a true statement. There are other interpretations that do not have 81 points, but they still satisfy my incidence axioms. All right, so just because there's a true statement about the game of set doesn't mean that makes it true in every model of incidence geometry. And to show you that, I'm going to create something right away that's not going to have 81 points. So not only is it not going to have 81 points, it's actually only going to have 4. Now that's different, right? It's different. Okay. All right, so this is called 4-point geometry. Our interpretation is that we have 4 points and we're labeling them A, B, C, D individually. We have lines that connect every pair of them. So there's a line AB, a line AC, and so forth. And incidence means belongs to, just like it did for set. I'm going to draw a picture of what 4-point geometry would look like. This is just one possible picture, but this is how you usually see it drawn. You can draw yourself a rectangle, and you can connect one of the diagonals on the rectangle. We will label our points as the vertices A, B, C, and D. And we need one more line. And all of a sudden now you realize that lines don't have to have this geometric image that said straight. We do that in Euclidean geometry, which we're going to talk more about very soon. But there's nothing here that said the word straight. These are my 4 points. You can check and make sure, do I have all 6 of those lines? Do you have 6 lines there? Yep. They're all 6 there. One of the ways you could check that pretty quickly is that each point, A, for example, has 3 lines coming out of it, right? So for every point, there are 3 lines coming out of it, or incident with it. But again, we don't get to say that this is the model unless we've actually checked the axioms to make sure that it works. And I don't think I actually have a slide on that. I think we were going to check them ourselves. Yes, we are. Okay, so let's double check our axioms. So what does the first axiom say? Can somebody flip back to it and read it to us? Incidence axiom number 1.
For every point P and for every point Q not equal to P, there exists a unique line L incident with P and Q.
Okay, so if I take 2 points that are different in my picture or on my description, is there a line connecting them? Yes, there is. So incidence axiom 1 holds very quickly, either visually or just checking the written down data because there's not very much of it. Incidence axiom number 2, somebody else read that one for us.
For every line L, there exists at least 2 distinct points incident with L.
Fantastic. For every line, and I have them written out, there's at least 2 points on them. Well, that's how I defined them, so we're good to go on that one. So incidence axiom 2 holds. Somebody read incidence axiom 3 for us.
I don't have like the full definition, I just have a condensed.
Okay, what's your condensed version, Shayna?
No line is incident with D.
Yes, so it doesn't have to be no line, but there exists a line. So change the word no in your description, but then you're good. So does there exist a line that is not incident with all 3 points? Yeah, none of our lines, in fact, do, right? All of our lines have only 2 points on them. So it's maybe even like a stronger statement than what this actually needed. So yeah, there's a line that doesn't have all of our 3 points, any 3 points on them. So we're good to go on that one. So we're good. Yay! This is an interpretation of incidence geometry. Not only that, but this actually satisfies the Euclidean Parallel Postulate. So I said that, but I haven't actually written it. You worked a little bit on your homework with the Euclidean Parallel Postulate. It's like on page 19 or 21 or something like that from your book. And you created a negation for it. So as a reminder, I've got the Euclidean Parallel Postulate written in here. For every line L and every point not on L, there exists a unique line, M, incident to P and parallel to L. And kind of like we did with our incidence axioms just a moment ago, confirming that that's true, we're going to confirm that this is actually true. I won't switch my slide just yet, but write this down and then we're going to double check it. Now our interpretation, our model actually, is small enough we could actually check this case by case. Okay, we're not going to check all the cases, but we're going to confirm it with a couple of them. So pick a line, any line. AB. All right, so Seth picked AB. And pick a point that's not A or B. D. Okay, so we've picked a line, AB, we've picked a point D. Which, if any of those lines, goes through D and not through A and B? CD, and it's the only one, right? This line, CD, would be parallel to AB through point B, D. And it's the only one that's possible. Let's pick another one. Somebody pick another line for me. AC. Okay, we've got line AC, and pick a point that's not on AC. B. We need a line going through B that doesn't go through AC. BD, right? That's the only option. And that's what the Euclidean Parallel Postulate said has to happen. For every line and every point you pick not on it, There's one line going through it parallel. One line going through it that doesn't intersect the first line you started with. And depending on what your history is with geometry and what you've seen before, most of you probably are under the impression that that should be very provable. And for Euclidean geometry, it is. I mean, this is one of the axioms of Euclidean geometry. We take it as a truth. You know, we hold these truths to be self-evident, that one kind of thing. Like, that's it. This is obvious. Super obvious. Why wouldn't it be this way? Well, there are two other parallel postulates that I want to introduce to you, and we will be using them later this semester. The first one is the elliptic parallel postulate. This is a good one. Parallel lines, they just don't exist. So that's kind of nuts, right? I mean, like, that just should have destroyed your entire picture of geometry right there. Because you've been working with parallel lines forever. We constructed them, didn't we? We did, with compasses and straight edges and some axioms and theorems and things that had been done before. Yes, we did. So these are the elliptic parallel postulate. Parallel lines do not exist. There's one more. These kind of go together, which is why they're together on the slide. The hyperbolic parallel postulate, also a fun one. It says that for every line, L, and every point not on L, there's not just one line parallel, there's at least two. At least two lines parallel to the original line through that point. And we will see models of this one as well later.
Will there be like a model that makes all three of those postulates true?
No. You have to pick one of them because they are opposite of, they're negations of one another. They say different things, so they can't be all true.
Okay, so this one is saying
There's more than one line parallel.
through.
Yeah.
And the first one says there's only one?
The first one, the Euclidean postulate, says there's exactly one. The elliptic says there aren't any at all. And this one says there's at least two.
So the first one is the one that you do in high school geometry.
The first one is the one we do in high school geometry, the Euclidean one, exactly, because we talk about Euclidean geometry in high school, exactly. A great circle of a sphere. This feels like an odd place to put this, but we'll need it here as we reference it later. So, on a sphere, a great circle of a sphere is a circle that goes complete, like if you imagine like a basketball or whatever, it's the line that goes all the way around the ball of thickest diameter, if you will. So a circle in a sphere contains the end points of a diameter. So if you were to take a diameter of your actual sphere, draw a circle connecting them, then you would actually have a great circle. Let me kind of mention why this is actually showing up in here. Imagine that you were doing what we would call spherical geometry. So you were doing geometry on a sphere. And your circles were these. I mean, your lines, rather, were these circles. I'm not going to go through and double check all the axioms and things like this, but just imagine. Points are just like we talk about points. They're just locations on the ball, on the sphere. But a line is the great circle that connects them together. Okay? Here's the problem. Every two lines do what on a sphere? They intersect. There is no such thing as parallel lines on a sphere if you're interpreting lines as great circles. So which of the parallel postulates would hold then? The elliptic one, the one that says parallel lines, they don't exist. What are you talking about? And in some sense, that should sort of resonate with you a little bit because, like, we live on pretty much a sphere, right? Earth. So that's awesome. You just thought that was going to create something crazy that didn't even make any sense, right? Well, you live in it. You live in the spherical geometry. I'm going to draw you a picture of hyperbolic. This is an example. This is called a disk model for hyperbolic postulate. Again, I'm not going to check all my axioms, but I'm just going to give you some sort of a taste of what's going on. So imagine you have a disk, and it's dotted on purpose because the boundary doesn't exist. Okay, it's not really there. Right? It's not part of the diagram. All the points are the Euclidean points inside. All right, so you've got points inside of here. You got lots of points inside. And you've got lines inside as well. And lines would go, something like this, right? So here's a line, and here's a point. And you want to talk about what would a parallel line through that point look like. Well, here's the problem. Parallel means they don't intersect, correct? I was working with my geometry class, my other geometry class that I'm teaching, and we talk about the fact that what I really just drew right there is a line segment. Agreed? It's really a line segment, but in this interpretation, that's a line. Okay, so this is not Euclidean interpretation, right? This doesn't follow with Euclidean geometry. That thing that I just drew right there is a line. Well, that means that this line is parallel to it. Parallel doesn't mean anything about distances. It means they don't intersect, and these do not intersect. Not only that, but this line is also parallel to the first line I drew. And in fact, with this particular model, I could draw infinitely many lines through that point that do not intersect the original line I drew, right? So again, I didn't check all my incidence axioms, but this is actually a model for hyperbolic geometry, which we will do more of later. These things don't not exist. It's just the interpretation that we've put upon our world that we live in.